All right, so now we got to talk about series circuits. What a series circuit is a cheap way of using one battery to power multiple lights. How do you do that? You say, here's what you do. You take your battery. Yay, battery! We plug in one side. We run it to a bit of metal. See the wire right here? It goes all the way to that bit of metal right there. Then goes through this, goes through the light bulb to that little tiny cruddy wire at the top of the light bulb. Then goes down this metal post, over to here, runs along this thing. This is just a loose wire, don't worry about that. Then it comes back in here, goes through this cruddy wire, whoop, out the back side, then runs along this bit of metal, then back down to here, then through this cruddy wire called a light bulb, then back down here and out the green thing, and then all the way back to dun 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 battery. Nothing's gonna happen until I go back to battery, right? But now back to battery, everything's lit up. Isn't that beautiful? You have 3 light bulbs lit up with one, count it, one battery. Now, what's interesting about this is I am going to remove one light bulb. I'm forcing every electron to go through every light bulb. If I remove a light bulb, what am I doing? Make a prediction. Unscrewing the light bulb. I'm breaking the circuit, right? Because I pulled out part of the circuit. It's gone. I've broken the circuit. Once I put it back in, the light bulb goes on. So, this is not how your house is typically wired because you don't want one light bulb to take out the whole entire house. This is how Christmas lights are done, though, right? Because you have Christmas lights, you don't want one burned out, one to burn down your house. So what they do is they rig them intentionally so one blows out, the whole thing blows out, you get ticked off, you throw away the light bulbs. And buy another one. Also another reason to put things in series. So this is called in series. Now what's true about series is this. When an electron leaves the battery, it must use up its energy between here and when it gets all the way back to the other end of the battery, right? It's got to use up all of its voltage, right? Voltage. It's a 6-volt battery. So it's going to use 6 volts getting there. So because of that, it's going to use them up at the worst possible places. 3 places it's going to use it up. These are the 3 places where it uses up making light and heat. Mostly heat. A little bit of light, which you can see. Now, this light and heat that it's making is coming from this battery using up its voltage. But each one of them must use some of the voltage to get through that, each one of these. Okay, so it's going to use some voltage to get through here, some voltage to get through here, some voltage to get through here. Now, the other thing's true, though, is this. The current coming out of the battery has to go through each one of these things, and it can't go fast an electron in front of it. So everywhere along this way, the current is the same. Every place along the trip is the same. Okay? Now, the reason why these light bulbs are very dim is because I'm making it go through 3 light bulbs. This poor little flashlight battery is only designed to light up one flashlight battery. I'm basically asking it to do it 2. So if I reduced the length it had to go, let's say I plugged it in, say, here. Let's hope this works. They would get brighter. They would get brighter. Because instead of using 2 volts per, because of the same size, and it's a 6-volt battery, each one had to use 2. Now using 3 for them. If I want to make it really bright, I don't know if you can both see this with this cute little camera I have, but whatever. I put it right here, and bam-o! Yeah, it is brighter. And that's a 6-volt. All 6 volts are being dumped through that one light bulb. That's probably going to break that light bulb, so I'm going to take it off quick. All right. Now, what happens if I had this little swingy thing here? Well, let's see if I can get the swingy thing to do what I want it to do. What? And I do this with it, so it is there. Now, I'm going to, let me first light up the 2 lights. Let me do the demo the correct way. Okay, so I have 2 lights lit right now, right? Because the electrons are forced to go through that cruddy bulb and through that cruddy bulb. But if I take this bit of metal, you can't see it because I'm not doing a very good demo here, this bit of metal, and I attach it here, why do the light bulbs go out? Because I made a short. Okay? Because I made it possible for the electrons to not have to go through the 2 cruddy bulbs. It instead goes through the bit of metal. It prefers the bit, so it goes through that. We call that a short. Okay, so it's a physics class. Because some of you like to do math in physics class, I guess we'll throw some math at you right now. All right, so how does the math look on this? Let's see if I can get my mouse working. Here it is. Okay, so in a series circuit, by the way, we're on the back of assignment 2, I feel bad, 9.3. 99% sure we're back at 9.3? Yes, we are back at 9.3. Double check my work. It says resistors in series, but above that we have something called DC versus AC, which we've not yet discussed. So, briefly, DC versus AC. DC versus AC. DC is direct current, means comes from a battery, essentially. It means that your electrons, when you put them on a wire, my power supply, right, and I've got my resistor, it means when you're taking DC, it means all your current is coming out of the battery, going through the resistor, and then going back in the battery, and that's where it stops. AC is a little different. Turns out it's cheaper if they don't have to do that. What they do at the power plant, and more on why they do this later, is here's your power supply, and your power starts to run this, your current starts to run this way, and then every 60th of a second they change the direction. What? Every 60th of a second they change the direction, which means the battery flips, and the positive side's down here, and the negative side's down here, and then 60 seconds later they switch it back. And so your electrons running through your wire, through your resistor, go this way, then that way, then this way, then that way, then this way, then that way, slowing down each time. Okay, so that's cheaper for reasons I'll get to in just a little bit, but it does lead to some problems involving things like computers. If you have a computer in the very back of your computer where you're plugging a power cord, you just have something called power supply. Power supply provides no power at all. In fact, if you don't have it plugged into the wall, your computer won't work. So what's a power supply do? What is that little, when you have your cell phone and you have your plug in the wall, and then you have a little box, and then you have it attached to your cute little cell phone, or sometimes this box is part of this little plug, okay? What is this box doing? Why am I paying for this box? I'm plugged in the wall to get power. Problem is your wall socket's AC, which means it would put current in one way into your phone and then back out, and then back in, then back out. That's a problem because you want your current to store up on your battery. So what happens is this little device switches, every time this switches 1/60th second, this switches 1/60th second. Well, a little trickier than that, but it's basically what it's doing. So, bottom line, DC, current's going one way, AC, current's going both ways, going back and forth. In the United States, switches every 60th of a second. In Russia, it used to be every 60th of a second, and then they used to set their clock. So we just, every time it switched directions, they would move it forward 1/60th of a second. Yeah, that's how they did it. And then they changed the speed at which they flipped it, and all bad things happened there. That's a discussion for another day. All things Russian. All right, moving forward. We're now going to do what happens with a series circuit. So we're going to go to the next one. Okay, so loosely described, we say in a series circuit, everything's forced to go through all of the resistors. So things get interesting. So let's say I have here a 60-volt battery. And over here I have a 2-ohm resistor and a 4-ohm resistor. Now, you might be thinking, Mr. Resnick, we've done this before. V equals IR. V is 60. I is I don't know. The resistance is 2. I get my currents equal to 30 amps. Well, and then down here I would simply go V equals IR. My voltage is 60. My current is I. Resistance is 4. So I would get my current is equal to 15 amps. Problem with that is twofold. One, can my amperage change? Can these electrons be going faster than these electrons here? Answer, no. Right? They got to push the guy in front of them, so they can't have difference, so that should really bother you late at night. Right? The second problem is this. This is actually more fundamental. It is, what about voltage? If I use all 60 volts getting from here to here, how much voltage do I have left over for the second resistor? Nothing. My electrons would pile up here because they ran out of juice. They used up all their energy. Can't go any farther. We're stuck. And that don't work either. So it's got to use it over the whole entire thing. So this is not an appropriate approach. We need a different approach. So the answer is, we look at this, and there's two ways you can fundamentally think about this, okay? There's the advanced course, which I'll do second, and the simple course, which I'll do first. When things are in series, the resistance total is equal to 2 plus 4. Essentially, it doesn't even know there's a wire in between, so what does it care? So 2 plus 4 is 6. Okay? Actually, so right over here, resistance total is equal to R1 plus R2 plus R3 plus ... Right? Because the wires in between don't matter, assuming they're relatively not cruddy. So therefore, if I've got resistance total is equal to 2 plus 4 equals 6, what's my current? Oh, well, then I just go V total equals I total R total. So voltage total is 60. Current total I don't know, but resistance total is 6. So I get my current is now equal to 10 amps. I'm going to check to see if that makes sense by saying if I have 10 amps going through here, that would be 20 volts I'd lose going through there. Then if I lose 10 amps going through there, I'd lose up the other 40 volts, and that'd be the total 60 volts I'm going to lose. So this is the correct approach for finding the current going through those two resistors. On the other hand, he says, the other approach, the advanced approach, could be using something called Kirchhoff's law. We're going to use a short version of Kirchhoff's law, which says, hey, I got 60 volts to give. I'm going to use some of it on the first resistor over here, right, IR. I'm going to use some of it on the second resistor, IR. Well, if I have 60 volts to give, I don't know how much current. My resistance is 2 for that first one. I don't know how much going through the second one, but I do know that I have the resistance is 4 for the second one. And then I recognize, first of all, these two currents are the same, right? They have to be, because whatever's going through this one has to go through that one. It's going to know what place to go, right? So therefore, it's going to be 60 equals 6I, I equals 10 amps, and that also works. Which one do you want to use? Whichever. They're both beautiful. They're both the kind of singing to the choir. Okay, with that in mind, I want you to get out assignment to print out, or already have it out, assignment 9-8. I want you to go ahead and do 9-8 right now. Number 1, please do number 1 only, and I will catch up to you once you pause and then hit play. All right, according to this, what I'm going to do is I'm going to say 3 20-ohm resistors are connected in series across a 120-volt battery. Draw the circuit. Here's my battery. I'll draw one up here, one over here, and one over here. You could draw as a line with 3 on this side, you know, whichever. So as long as there's no extra weird routes, right? It's going to all work. This is 20 ohms. This is 20 ohms. This is 20 ohms, and I have 60 volts. Here we go. So the first thing I want to do is find my resistance total. Resistance total is equal to 20 ohms plus 20 ohms plus 20 ohms. That gives me a total resistance of 60 ohms, which, when I do voltage total equals current total times resistance total, gives me 60 equals I total times 60, or the current going through each one is 1 amp. Oh, sorry, what's effective resistance? That was what I was supposed to solve for. I totally skipped that step. So part B, what's effective resistance? It's going to simply be 60 ohms. What is the current through the circuit? That's what I just solved for down here already by saying voltage total equals current total times resistance total. By the way, I could still do it using a more advanced approach, Kirchhoff's law, where I go I times 20. Pen's not working. Come on, pen. Oh, now I got 3 lines there. Okay. Plus I times 20. So I'm getting 60 equals 60I, which gives me I equals 1 amp. I could do it that way as well. Okay. Try number 2. I'm pretty much, yeah, let's do number 2. Okay, try number 2. Pause this, do number 2. All right, here's number 2. Let's see if I can get this done before YouTube times me out. I've got effective resistance of the circuit, so I'm going to RT equals 10 plus 15 plus 20. I get that my total resistance is 6, that's not 60, that's 35, 45, 45, no, is that right? Hold on, 15 and 20, oh, this is 25, that's why I'm messing up. Okay, let's try this more. 50 ohms. Is that good? That's my total resistance. Okay, that's step 1. What is the current through the circuit? Well, V total equals I total times R total. My voltage total is 90 equals I total times the 50 resistance total I found so far. So I total is equal to 1.8 amps. Okay, what's the current flowing through each resistor? Well, what flows through this one has to flow through this one, which has to this one. So the answer is 1.8 amps is happening everywhere. Has to. There's no off ramps, no on ramps, whatever. All right, try problem number 3. Stop after 3 to watch the next video. Okay? Great.